We are now going to focus on determining the domain and range given any relation or any function. You may want to pause the video real quick to copy this down. I like to use the acronym Dixroy to help me remember that the domain is the set of input or x values. Of course, don't ever repeat. And the range is a set of output or y values. So domain and x's, range is y. So when we go to take a look at our next page here, or our example problems, we also need to be able to differentiate between having a discrete relation and a continuous relation, because that affects what our domain and our range is. So in a discrete relation, that means that the dots are not going to connect. They're going to be individual numbers. A list of numbers will be given to you, and those are the only numbers that are part of that relation. If you were graphing them, then you would just have a bunch of dots. They may or may not be in a line. You might have one random one out in the corner, but they would not be connected in any way, shape, or form. And when we write the domain and the range for these, we write individual points. So 3, 5, 2, okay? Same for the range. It's individual points. A continuous relation, though, has actually an infinite number of dots. And so we write the domain and the range of those as an inequality, or it can be written as all real numbers, because we can't possibly list all of the different values in that domain or in that range. So you may start out plotting points like what you did in Algebra 1, but you're actually connecting all of the dots because it's a function or a relation that's continuous. Now, we can use, when we are graphing, we can use a vertical line test to help us determine, is this a function or not? But the vertical line test ultimately is only a shortcut. It is never a justification. So when you are looking at a graph, whether it be continuous or discrete, you can use the vertical line test to say, yes, quickly, it is a function. It's not a function. But you may not use the vertical line test as when we have to say why or why not. You can't say it passes the vertical line test or it fails the vertical line test. You need to indicate what the vertical line test was actually testing. Okay, and the vertical line test simply says if you take a vertical line that's up and down and you drag it across a graph, that graph should only be touching the line once at any point in the graph. So no matter where I stop it, it touches it only once. I'm going to go ahead and change this relation here to give us an example of something that maybe isn't a function. Here, no matter where I stop it on any point, I should be only touching the line once. But you can see here with the dot that I added, now I'm touching it twice. That would mean that this is not a function and this is a function. Now the reason why it's not a function, what are you looking for when something is functioning? You are looking for, does every x have only one y? If every x has only one y, then that means it's reliable. It's a function. And we use the word function in our everyday life too. If you have a functioning car, then that means that it is a reliable car. When you turn the key of your car, the expected thing to happen is that your car turns on. If you turn the key in your car and sometimes the car turns on and sometimes the horn honks, I would call that a not functioning car. It is not a function. Okay, every input or thing that I did to the car did not have only one reliable output. We expect that when I put the car in reverse, it's going to go backwards. If I put the car in reverse and sometimes it goes backwards, sometimes it goes forward, and sometimes it just stalls, it's not a functioning car. What when I did something to it, it did not give me a reliable single output. We can relate that back to our relations here by saying that the input value, or the x values, there can only be paired with one single y. Let's take a look at this example here. We'll first list out our domain and range, and then we'll decide, is it a function or not? So for our domain, it's all the x values, and we're going to be careful not to repeat. Now this technically is a mapping diagram, so it's not going to have repeats anyway, but looking at these x values, I have my domain, -4, -1, 0, 2, and 7. I know my finger or my hand was over that, but you have it on your paper too. That's my domain, easy peasy. I know that I can list individual points because this is a discrete example here. It's a discrete example because it just listed individual points. The range is all the y values, or in this case it's listed as f of x values. They're the same thing. The y values are -5, 0, 1, 2, and 4. So we need to decide, is this a function or not? So we're going to look at each of these x values and decide, does it have only one y value? And that's kind of why it's important that when we have a mapping diagram, we don't have a repeat of either of the values, so that we can look at it quickly and tell. If I said, what's paired with -4, your only option to tell me is it's paired with 0. If I say, what's paired with -1, the only option to tell me is it's paired with 1. What's paired with 0? -5. What's paired with 2? 4. What's paired with 7? 2. Okay, because each of those had only one number that it was paired with, that means that yes, it's a function. Our reason why? Every x has only one y. It's a phrase that you probably should just commit to memory, because every time you determine something is a function, the reasoning is the same. Every x has only one y. You may want to pause it while you're writing that down, because I know my hand kind of covers. But we're going to move on and look at this graph now. So I need to list the domain. It looks like a discrete graph to me. There's only individual points. They're not connected in any way, shape, or form. So I just need to figure out, what is the x value to each of these points. -4. Next one, -1. Next one, 2. And finally, we have 3. X's move left to right, so I just start on one side of the graph, either the left or the right, and look at the dots in order so that I can make sure I don't leave any out. Let's look at the range. So those are up and down, so I'm going to start at the bottom. And I see that this dot is going to -2. This dot goes to 1. This dot, the y value is 4. This one, the y value is 5. Now, since it's already as a graph, I'm going to use my little shortcut. And I'm going to drag a vertical line across. You can use your pencil or your hand. And if at any point it's touching more than one dot, then it's not a function. So 1 dot, 1 dot, 1 dot, 1 dot. That means yes, it is a function. And our reasoning why? Every x has only one y. The next one is just a list of points. It's not written as nicely as a mapping diagram. So in this list of points, we're going to look and see what's the domain. So I'm going to write all the x values down. -2, 0, 1, and 6. Now right off the bat, there weren't any repeats as I was going through that. So I could jump right ahead and say, hey, yes, you're a function. Let's look at the y's. 3, 4, 1, 0. Notice I was able to say, yes, this is a function before I even looked at the y values. Frankly, I don't care how many times a y value is repeated. It'll always be a function as long as every x value isn't repeated. And in the real world, we see examples of that too. Most of us probably have a light switch or a light in our house that's controlled by 2 different switches. If in my house, I have one light in the living room that's controlled by a switch by the hallway and the other switch is over by the kitchen. If I flip the switch that's by the hallway and the light's off, I expect it to turn on. If I flip the switch in the kitchen and the light's on, I expect it to turn off. It has an expected output, and even if it was off, I would expect it to turn on no matter which switch I flip. So 2 different inputs had the same output, but I still have a functioning light. Okay, and we'll see that example in just a minute. But here, since it's a function, that means that every x has only one y. And if you need more examples in class, just ask. I'm more than happy to provide those examples for you. Let's take a look at another discrete one, and then we're going to move on to continuous. So in this discrete one, let's write our domain down first. So our domain, we have -5, -3, -3 again. Uh-oh, that's 2 x's that are the same. So I know right off the bat, this is not going to be a function. And I'm not going to write the second -3 down because we don't write repeats. I'm going to skip over it and go down to 0, then 2, and here's a second 2, so I'm not going to write it down, but it just confirms, yep, not a function. And what's your reason why it's not a function? Every x, this time, does not have only one y. Now let's look at the range. I have a 6, -5, another 6, not going to write it down, 0, and -3. Now I'll give you another example here. We don't have to write the whole thing down, but I will give you an example of something that is a function, but it has a repeat in the y values. So just a quick extra example here. You don't have to write this one down. It's just to help us out here. So 0, -1, 2, and 3. Let's say that 0 is paired with 1, -1 is paired with 2, 2 is paired with 5, and 3 is paired with 1. Okay, this is still representative of a function because every x here is only paired with one thing. 0 is only paired with one thing. 3 is only paired with one thing. It's okay that they're paired to the same thing. That's like a light switch in the kitchen controls the light in the living room. The light switch by the hallway controls the same light. It's still a functioning light. Okay, so that's just an extra example for you. Let's take a look at continuous graphs. Now, discrete graphs are the easiest ones to write the domain and range for, but sometimes they can be the hardest ones to tell whether or not it's a function. But continuous graphs are a little bit more challenging to tell whether or not it's what the domain and range is because we have to deal with an inequality. So what I like to do with a continuous graph is I know with domain, I'm looking at the left and right side because domain is all the x values and our x-axis moves from left to right. So I'm going to look on the far left and I'm going to decide what is the furthest left that this graph goes. And the furthest to the left that this graph goes is -2. If I follow the graph all the way over, what's the furthest to the right that this graph goes? You're kind of writing down the extremes of the graph. The furthest to the right that the graph goes is all the way to 4. And the graph is actually in between there, right? The x values for this graph are in between those two numbers. The x values are bigger than -2 and smaller than 4. As long as you write the smallest one on the left and the largest one on the right, it will always be two less than signs. And we know that it's equal to because it actually touches those two places. Let's take a look at what the range. Range is up and down because the y-axis moves up and down. So I'm going to find what's the smallest that it would be. What's the furthest down that this graph goes? It goes to -3. What's the furthest up that it goes? And it hits 4. And the graph, or the y values, are somewhere in between that. Smallest on the left, largest on the right, so two less than signs. And they actually do touch those numbers, so I'm going to include an equal to. If you've done this right, you should have a box around your entire graph. Okay, there shouldn't be any part of your graph that's out. And we can decide if this is a function or not by using our shortcut, because it's a graph. So no matter where I stop this, it'll always touch the line only once. So that means, yes, it's a function. And the reason why, every x has only one y. Let's take a look at the next one. Domain furthest left. And you kind of have to squint just a little bit, but the furthest left that it goes is -6. The furthest right is +6. And x is somewhere in between. Oops, sorry, I'll move that over a little bit. X is somewhere in between there. So I've got less than or equal to. For the range, the smallest value is at -4. The largest value, or the highest it goes, is at +4. Y, because that's range, is somewhere in between. Less than, and it touches, so it's equal to. Is it a function or not? Get your vertical line out, and you can see right off the bat, it's touching in two locations. Once here, once here. That means that the answer is no, it's not a function. But your reason is not it fails the vertical line test or it touches the line more than once. Your reason is every x does not have only one y. Let's take a look at the next one. Furthest to the left, furthest to the right. So I have -2 for the left and +4 for the right. Notice they go on the left and the right side. X is in between them. Two less than signs, but this one has a closed dot, so it's equal to. This one has an open dot, so we don't include an equal to sign. Let's go with range. Lowest is at -3. Highest is at 3. Y is in between. Close that, so less than or equal to. Open that, just less than. So is it a function or not? Handy dandy vertical line. And it only touches once, no matter where I'm at. So yes, the reason why, you'll get tired of hearing me say it. Every x has only one y. Couple more examples here. Just a reminder, if you think you've got a handle on it, go ahead and pause the video, try the problems, and skip ahead and see if you're getting the answers right. So furthest to the left, 0. Furthest to the right, oh, this has an arrow, so there isn't a furthest to the right. It continues on forever. Now, you can go ahead and write your symbol here and put your x and change it into Venn form. So x is greater than 0. Or you can recognize that all of these x values are greater than, so you can automatically write it as x is greater than 0. I don't really have a preference as to which way, as long as you eventually get back to here. So this time that inequality didn't have an end point. When it doesn't have an end point and it ends in an arrow, your inequality will change and it won't have an end point either. So let's look at the y's. We're going to have a similar thing happen. The smallest that y can be is 0. And the largest, there isn't one, because this arrow, I know it only looks like it's pointing to the right, but you'll notice from the trend on the graph that it's getting higher and higher and higher each time. So if I were to extend it, it is going to keep going up and up and up and up. And it will go forever. So the highest that it can be isn't known. So we have to say that y is greater than 0. Again, you could do the same thing. Write it like this and then flip it around if you struggle with your inequalities. Is it a function or not? It only touches once. That means yes, it's a function. Every x has only one y. Take a look at the next one. We see something else happens here. So our domain here, when I go to find the furthest left that it can be, I notice that there's an arrow. When I go to find the furthest right that it can be, I notice there's another arrow. So I don't even have any numbers to write down here. That means it's one of those special cases. It's one of the things that I underlined on the other page. It's called all real numbers, meaning that any number that's on this graph, like this coordinate plane, will always be part of the graph. Now, I use a symbol for all real numbers because it's a long time to write out all real numbers every time, and I don't like to write a whole lot. So the symbol that I use, you draw two lines next to each other, kind of like parallel lines, and then you are going to make it into like an R. You could also draw an R and then draw an extra line inside of it. Either way, but this means all real numbers. Looking at the range, though, I have the number that's the furthest to the bottom, and it's at -3. But when I go to find a number to the top, I've got arrows again. So y has to be greater than those numbers because all of these other y's are bigger. Again, you can write it as an inequality and then flip it into Venn form if you'd like. And I did just notice that on this previous one here, I forgot my equal to signs. So I'm sorry if that confused you back there. Or you were asking, why aren't there equal to signs? I just forgot. All right, let's find domain and range of this one. So domain, I'm looking furthest to the left. Here it is. The furthest to the right, don't be fooled, it's not right here. You would be crossing right over the graph, and we don't want to do that. It's right here. So furthest to the left is -3. Furthest to the right is +3. X is in between. So 2 less than signs. And it actually does touch those locations, so we're going to put equal to's. Let's do the range. Furthest to the bottom, -4. Furthest to the top, just a smidgen over 5. And I will say that there's most of the time, anything that I would give you is going to cross at a nice place. Most certainly on a quiz or test, it will be something that crosses at a nice place, but this one just doesn't. So we're going to just round it, 5.2, somewhere in that range. Y is in between it, 2 less than or equal to's. Is it a function though? Well, as soon as I put that vertical line, I can tell that it touches in 2 locations. So new, every x does not have only one y. Go ahead and take a look at your assignment. There is one problem on there that you are not able to tell the range because there's not markings on the graph, so you can skip the range for that specific problem. If you've got questions, feel free to just email me or ask them in class tomorrow.